Hey guys, welcome back. So in this second video of our econometrics playlist that we've got going here, we're going to go over the math behind deriving our linear regression OLS estimator that we talked about in the previous video. This video is not going to be so much about the R or the R programming per se, which is the general theme of this YouTube channel, but I will say this: if you would like a copy of the RMarkdown file that's used to produce these slides, I'd be more than happy to supply them for you for free. Just reach out to me, and if enough people do so, then I'll leave a permanent link down in the comments below. Alright, so we talked about linear regression in our last video, and we said that we can, the purpose of it is to explain underlying relationships between one or more variables. And we put together this first initial line of math that we see here on this slide here, where we said we have a dependent variable y, and we have individual observations with the little I subscript there for many individuals. And we're going to express this dependent variable as a function, more specifically a linear function, of our independent variable x. And the full magnitude of this linear relationship is going to be governed by the sizes of beta 0 and beta 1, beta 0 being the intercept and beta 1 being the slope term. Now, we plotted in our last video a whole bunch of cases of individual points, and we showed that in some cases we have a line of best fit through the data, so that some individuals actually fall on that line, in which case then the error term, the little e component of that first line, is relatively small. And then some individuals were outside of that realm, and so then the individual error term for that one observation might be relatively large. So we can take this regression equation, this econometric model, if you will, and we can completely reverse it, and we can solve for the actual error term. Now, many things within statistics are actually much more important if we think about it in terms or context of the error term. It actually ends up being the easiest way to compare different types of models. This looking at the actual error, the portion of the model that is not explained, is actually relatively important. In fact, we can even think about this first regression line as saying, okay, we have something that we're trying to explain. We have this portion that we're able to explain, which corresponds to beta 0 plus beta 1 times xi. And then we have the component that we cannot explain, the irregular part, the error term. And so here we solve for this portion that we can't explain. We take what we have, we take what we're trying to explain with it, the systematic component, if you will, and then we have the error term that's attached to it. So in terms of actually trying to mathematically solve for beta 0 and beta 1, there's a couple of different ways that we can go about this. This is an algebraic problem. It's a linear problem. So we could express this strictly in terms of algebra without any calculus whatsoever. But I think it might actually be beneficial to at least set up the calculus problem, to at least think about this as an optimization problem. Because once we extend beyond basic linear regression, which is really the value of statistics, then we're going to have to get into this realm, so we don't have a choice. So we might as well think about the linear regression case in the context of an actual unconstrained optimization problem. And what I mean by that is we're going to pick values for beta 0 and beta 1 that satisfies a condition. More specifically, we pick these values minimizing the sum of squared residuals. And I mentioned in the last video how we have some type of vertical distance between an individual observation and the line of best fit. And I said if we can't get a better line from a linear regression standpoint, if we pick any other values of beta 0 and beta 1 that intercept in the slope term, we actually end up, if we calculate all the vertical distances between those observations and we square them and we add them up, we actually get a worse number. And so this is the math behind that. This is exactly what I was implying in that video. We have a minimization problem. We're going to pick values beta 0 and beta 1 such that we're summing over all of our individuals from 1 to n the squared residuals. And so you can see yi minus beta 0 minus beta 1 times xi, which is exactly what we have for our error term here. So this is the reason why I want you guys to think about this from an error perspective, or the component that we can't explain. We're trying to minimize the amount that we can't explain. And so the only way to do that is, of course, then to square it so that we don't have positives and negatives kind of weighing each other out. So we square all of those differences so that everything is positive, and then we minimize that and pick the values of beta 0 and beta 1 that specifies this unconstrained optimization problem. Now, another thing to kind of keep in mind here, and for my calculus nerds, they'll understand this right off the bat. For those people that aren't quite as familiar with calculus, you'll understand this possibly to a slightly lesser degree. But since we have two arguments that we're trying to solve for, beta 0 and beta 1, we have two first-order conditions. We have two equations. So this is going to be a system of equations. In this case, we have just two equations and two unknowns, but it will be a just identified solution in order to solve this problem. Now, there's going to be something related to that towards the end of the video, but I wanted to at least bring that up now. Now, at this point, a lot of textbooks trying to avoid the calculus problem immediately jump into solving this from a series of summations. So you have a whole bunch of summation notations, and in order to get to an algebraic solution without talking about that calculus problem, because they feel like the calculus kind of scares you. But to me, I feel like the calculus honestly kind of makes it easier. But given that the majority of people, and it's particularly people that are looking at this channel, they're familiar with programs like Excel or other data science programs, definitely so within R, we're used to thinking about vectors of numbers, columns of numbers, arrays, or matrices of numbers. And I think this is much more intuitive to think about this from an actual matrix perspective. So I've taken our regression equation and I've kind of redefined it in matrix form. So instead of seeing lowercase y with a I subscript here, now I'm defining capital Y as a vector of individual y observations, where we have observation 1, observation 2, all the way to observation I. And then we're going to specify our X matrix, where here we have a column of 1s, we have x1, x2, all the way to xi. Now, the reason why we have a column of 1s is because this is going to be the column that corresponds to beta 0. And so we want to make sure that we're picking a value for beta 0, our intercept, that is the same for every observation. So that's why it's multiplied by 1. This column, the second column here in our X matrix, this corresponds to our parameter value for beta 1. So it's going to be varying according to how X varies and X moves. We combine beta 0 and beta 1 into one vector that we call beta, and then of course we have our error terms E1, E2, all the way down to EI. And so this equation perfectly summarizes our previous regression equation from the last slide here. But whereas this econometric model is expressed in individual observations, this econometric model is expressed in vectors and matrices. All right, so as a result of that matrix formulation, we can re-specify our minimization problem to be the following without any subscripts here. So here we're going to minimize picking our values in our beta vector according to the sum of squared residuals. Now, the reason why this doesn't have a summation notation is because if you, as my students, you should have already looked at Appendix A and Appendix C, which covered a lot of the mathematical notation from the textbook. You guys know that whenever you're dealing with matrix calculations, whenever you're multiplying a matrix and vectors together, given that they're appropriately sized, you're doing a series of multiplication problems and addition problems. And so that process of multiply, add, multiply, add, multiply, add, within matrix calculations means that we automatically get all of the summation built into this. So we can specify both of our regression equations inside of a matrix form. So we have basically our first equation and our second equation for our linear system here. And this is all expressed now in matrix form. Now, I want you to kind of break apart some of this a little bit. So I'm going to kind of back and forth between this slide and the previous slide. So we have this first term here kind of hanging out here, where we have n's and summations of x1 or xi on the off diagonal elements, and then of course on the main diagonal elements we have n, and we have the summation of xi squared. So if we actually take our vector, or pardon me, our matrix x prime I. So here x prime is going to be the transpose of x. So the transpose of x times x, we end up with the following calculation. Here we've transposed what was our original x matrix, and we kind of turned it sideways, if you will. And when we actually take this calculation and multiply this this matrix through, we end up with the following initial matrix that we had previously in the last slide. Likewise, for x prime y, the transpose of x times y, we have the exact same type of calculation, and we end up with the other side of that equation. So here you can see exactly how we solved for both of these, this vector here and this matrix here. All right, so we can summarize some of this calculation. You first need to understand that from a matrix algebra perspective, there is no such thing as division, but we can solve for beta by pre-multiplying by the inverse of that. So if this first portion here is x prime x, this is beta, and this is x prime y, then this allows us to pre-multiply by x prime x inverse on both sides of this equation. When we do so, the product of x prime x inverse times x prime x is equal to what we would call an identity matrix. And in matrix terms, this is the matrix equivalent of multiplying by 1. And so we are left then with an estimate for beta hat equal to x prime x inverse x prime y. And this is a relatively well-known result. We see this repeated a lot within linear estimators, and not just with ordinary least squares linear estimators, but with all other kinds of linear estimators. We see some variant of this x prime x inverse x prime y solution for our beta vector. Now this does require us to take the inverse of a square matrix, which mathematically might be a little tedious, particularly if you have a whole lot of individual values or observations, and hopefully you do have a lot of observations. So we clearly want a computer to do this, but it's relatively important for us to understand how we get the solution for our beta vector or beta hat. Now, once we have beta hat, it doesn't take us long for us to be able to solve and reverse engineer our original matrix notation equation to solve for the error term. And once you actually have observed errors, plugging in the actual your estimates for beta hat, we have our observed y data, we have our observed x data. Once we have our estimates for beta hat, we can actually back out then our residuals. And once you have your residuals for your regression equation, you have pretty much everything you need between those two components here. So we can use that in order to calculate a variance covariance matrix. From the variance covariance matrix, we can take the square root of the diagonal elements of that, and we can actually get to standard errors. So it's relatively easy once we have that those individual components here. E prime E is going to be an individual scalar calculation. We have I that's going to end up be the number of individual observations. We have K the number of parameters, so we can get sigma hat squared relatively easily. Once we have x prime x inverse, of course, multiply that by sigma hat squared, we end up with our variance covariance matrix. That's of size k by k. It's going to be a square matrix. And then, of course, the square root of the diagonal elements of that give us in our standard errors. From standard errors, we're able to do hypothesis testing, which we will dig into as we progress forward into this this kind of online feature or online course. And then we also are able to calculate this number that we call R squared, and also its contemporary adjusted R squared. R squared represents the percent of our observed data, or our y variable or dependent variable, that we're able to explain with our systematic component, with our model. So clearly that's going to be a function of what we can't explain, and it's going to be a function of our actual data that we have for y. So we get this number. Usually it's reported in decimal terms, but it can be converted into percent terms relatively easily. Adjusted R squared is a little bit more tedious to calculate, But it actually is going to be something really important as we move into examples of linear regression where we have other dependent or independent variables. We have more than one x variable. We, of course, have a larger system. We get more parameter estimates. We may move from beta 0, beta 1, beta 2, beta 3, etc. But as we add more and more variables, we inherently tend to explain greater and greater and greater portions of y, even if it doesn't belong there. And so adjusted R-squared has this additional penalty for including variables that may not be perfectly suited for this model. So we're kind of penalized for possibly overfitting our data. And that's where adjusted R-squared comes from. Some interesting results about OLS. Once we kind of get to past the math, I know that's a whole lot to kind of go through, especially for undergrads predominantly. We should probably follow this up with some interesting tidbits of information. The first is going to be the sum of the residuals, the sum of the error that we end up solving for or backing out. Once we have our beta hat estimates, they're going to sum to 0. That should be the case. If we have well-behaved data, we end up with a line of best fit that, yeah, the sum of all our residuals should be 0. Additionally, if we have well-behaved data, the sample mean of our residuals is going to be equal to 0. Now, the reason why I talk about both of these is because that's going to be kind of important when we are assessing whether our data is normally distributed, or particularly our dependent variable, our y variable, when it's normally distributed, which will also impact our error term, but we'll get to that later. The hyperplane of our regression is going to pass through the mean values of both our dependent variable y and our independent variable x. That's going to be kind of interesting and important. So, in fact, if you actually broke out all of the algebra to solve for beta 0, you'd find it's going to be a function specifically of the average value of y and the average value of our x variable. The predicted values of our dependent variable. We can basically solve for these imposing that e is 0 for every single individual, and so then we can actually solve for a hypothetical predicted value of y for our model once we have beta 0 and beta 1. And this is going to be uncorrelated with our residuals, with our error term. That's going to be something that's kind of an interesting feature of OLS. The mean predicted values of our model predicted dependent variable y is going to be equal to the mean of our observed data of y. So the hypothetical dependent variable is going to equal to the actual observed dependent variable. And given that our model is truly linear in functional form and in parameters, there is no better estimator. This is as good as it gets. Now, this inherently implies that we have some assumptions built into this calculation, and I would be horribly remiss to not cover that. So this last slide is going to kind of cover all of our OLS assumptions that are kind of needed in order for us to do this calculation. 1 through 5 are explicitly needed. 6 is kind of quasi-needed, and I'll talk about that. All right, so the first is going to be that the mean of our errors sums to, or the mean of our errors is 0 for all. This usually ends up being the case. It doesn't always end up being the case. If we have really ill-defined data, then this does not. If we have data that's exceptionally heterogeneous, which means that it's kind of clustered. You have a cluster of individuals for our x variable, and then they're also clustered again for another group of individuals, and it may be that this doesn't actually behave well, and that ends up posing a problem. And so it's entirely possible that we can violate that given some examples. We are also assumed that we have a constant variance, that our calculation for sigma squared is the same for all samples, and that may not be the case. Additionally, it may not also be the case that we may have 1,000 observations, and then we add 500 more observations, we may get a completely different estimate for sigma squared. And so if that's the case, then we don't have a constant variance within our subsample, and we need to do things in order to correct for that. Third is uncorrelated errors, which basically means that the individual errors are not correlated among themselves. Again, this can be accounted for. This can also be tested for, but it's kind of a baseline assumption that whenever we're calculating a linear regression model, that these error terms, these unexplained components in our model, there's nothing systematic there. We would like to think that as the researcher, we put together a model good enough such that whatever's left over of y that we can't explain, it's not important. But clearly, if you miss something that is particularly important to explaining our y variable, then whatever you have left over, that's where that goes, which means that there may be some type of systematic component there. If you can predict something out of your error terms, you've misspecified your model, and that's something that's always good to kind of keep in mind. It's real easy for us to put together really bad examples of statistics, and it's really easy for us as the researcher to possibly do something that we shouldn't do, or put the statistics in a bad position, if you will, torture the data. So I've always said this among my researchers, going into statistics is an incredibly morally centering exercise. You have to be morally centered here, because it's real easy for us as the researcher to omit something, and when we omit something, we may possibly be doing something wrong. And if we don't go back and we don't have other people going back and checking on us and checking on our work, then it's entirely possible for us to skew results in really unethical ways. Number 4, there's independence between the error term and the regressor. So we have our individual errors and we have our regressors. There should be no relationship here. Economics is terrible about this. There is correlation between error terms and regressors all the time. Usually, though, what I tend to find the most out in the wild with actual observed data is our model is misspecified, which means that there's a systematic component in our error term, and that's why we're seeing that correlation. Really what's happened is most likely something's been left out of a statistical model that already would be highly correlated, and so then that would fall into the category of number 5. Number 5 is our individual x variables are uncorrelated. Now in this case we only had one x, so we only had beta 1. We didn't have beta 2, beta 3, beta 4, and so on and so forth. So we didn't really have to worry about number 5. When you only have one independent variable to explain our dependent variable, then this number 5 is not really that important. So it's kind of further down on the list. But as we get to more and more complex models, it's real easy for us to just grab another variable and put it in there. And when we do, we have to make sure that these x variables are not correlated amongst themselves, because if they are, then this is going to bias our estimates for beta. Finally, our last one is normality of errors. Now, this one is a special one because it's not explicitly needed in order to calculate an OLS regression. However, it is needed in order for us to do hypothesis testing. And we're going to get to hypothesis testing in a later video, so hold on. But until then, kind of keep that in mind. This whole normality of errors thing, that's something that's imposed through statistical inference, not so much the actual mathematical calculation of beta 0 and beta 1. I hope this video was helpful for you, and hopefully it kind of clears up or demystifies some of the mathematical notation and the actual calculation portion behind OLS regression. If you have any questions about it, put them in the comments below or message me directly. And like I said, if you want a copy of the actual RMarkdown slides or the source file for these slides, by all means, just send me a message and I'll make sure to get a link to you. Thank you so much for watching.